Okay, let's get started. How was your exam?
I think it went well.
Okay,
Pretty good.
okay, great, yeah. Um, so I'll be discussing the solutions for the midterm exam one. I have prepared it for you. Let me share the screen. Everybody, can you see the exam paper?
Yes, sir.
Okay,
Yes.
okay, great. So you see, so this is the question, and then below of each question, so I have written down the solutions. Uh, I have provided the solution to the grader. I think still he has not started making grades. Hopefully soon, in a day or two, it will be ready for you. I will let you know. Um, you see, the first problem was for this circuit, find out I0 plus, V0 plus, di0 plus by dt, dv0 plus by dt, and I infinity and V infinity. So you look for I0 minus. First, I am calculating I0 minus because that will be the same value for the I0 plus. So when the switch was closed, then what happened? This inductor was shorted and the capacitor was open circuited. So therefore all the current was flowing through the 2 Henry inductance only because that was shorted. So this means the current was 12 over 6, which is 2 ampere. And then voltage again 4 ohm will not be taken into account because it was open circuited. So ultimately voltage across capacitor means voltage across the 6 ohm resistors. This is one point and this is other point essentially. So 2 ampere current was flowing, so 2 multiplied by 6, that is the 12 volt. So therefore accordingly the first answer I0 plus and V0 plus is the 2 ampere and 12 volt. I think everybody understand this one. And then at the last part, I infinity and V infinity both will be like 0 ampere and 0 volt. The origin is that that switch is getting opened at t equal to 0, and then transient happen. But infinity means after a long time at steady state condition. So at some point, what will happen after a long time? All the stored energy will be consumed up, will be dissipated by these resistors. So ultimately, current will be 0, and then voltage will be 0. So that's why I infinity 0 ampere, V infinity 0. Now the di 0 plus by dt and dv 0 plus by dt, for that, see what I am doing. IC 0 plus CB dv 0 plus by dt. So I have to find out dv 0 plus by dt, which is IC 0 plus by C. And then there will be the minus sign. So because you see, this is plus minus, but here it is minus plus. So accordingly, so there will be minus sign here. So IC0 plus means this 2 ampere. So therefore minus 2 over C value of 0.4. So minus 5 volt per second. This will be the answer. And then for the inductor, you can write VL0 plus is L di by dt 0 plus. So this means you need to find out di 0 plus by dt, which is VL0 plus over L. So and then VL0 plus, from here, I am writing the KVL for this loop. If you write the KVL for this loop, and you can sum up 4 plus 6, that is the 10 ohm. So 10 ohm, 2 Henry, and 0.4 farad. And then you can write down the KVL equation. So 10 multiplied by 2, this means 2 ampere current was flowing through this 10 ohm resistor, that one. Then VL0 plus across the inductor, and then capacitor minus 12, because this is the allotted directions, given directions, minus 2 plus, that equal to 0. That is the KVL. So from here you are getting VL plus is that 12 minus 20 minus 8. That minus 8 I am substituting here. So therefore minus 8 over 2, this is minus 4 ampere per second. So therefore we all are done. So dv0 plus by dt minus 5 volt per second, and this one is minus 4 ampere per second. And this is one answer, and on the top I0 plus and V0 plus is another answer. I think everybody did this properly, right?
Yes.
I missed the negative signs on part B for both those.
Okay. In both cases?
Yes.
Okay. So probably the grader will cut a little bit, maybe 1 credit or 2 credit.
So it's negative because it's dissipating, correct? So if I ever see a circuit that I know is going to go to 0, I can assume they're going to be negative.
Yeah, so therefore, for example, see, this is the current direction for this loop. Like, therefore, you can plus, minus, then plus, minus. This will be the voltage drop. But then here it is like minus, plus. It is given. So that's why. So if it would be like plus, minus here, then it would be plus sign there. There is no change. But because it is minus, plus, and then this is the, you see, current direction I. So therefore, all voltage drop plus, minus here through this resistance, even plus minus, all are fine, but this one is like minus plus. That's why you are changing the sign here and then same region here. So does this make sense?
Yes.
Yeah, okay. So therefore, still I have not uploaded this solution. Right after the class, I am going to upload these solutions for the exam under the same tab, exams. I mean, you can see the question paper, and then it will be like solutions for midterm exam on. This will be the title of this PDF file I am going to upload. So later again, you can see. Okay, and then now moving forward with the next one, find the Thevenin equivalent circuit at the terminal AB for the following circuit in figure 2. So the circuit was not difficult. It is simple circuit. So first you have to find out G Thevenin and later like V Thevenin, two things. So to find out the G Thevenin and looking from terminals A and B, what you are looking? You are looking that 10 ohm, and then you are looking this point. And then also what you have to do, because this is voltage source, you have to make it short. So therefore once you make it short, so this means your J20 and minus J10 will be in parallel, and that parallel combination will be in series with 10 ohm. So therefore see, I have written here J Thevenin, that J20 parallel minus J10 plus this 10. And then I am calculating. So I got G Thevenin in rectangular form 10 minus J20, or in polar form 22.36 angle minus 63.43. And then now I need to get the V Thevenin. This means the voltage across these 2 points. So, but everybody see, when this is the source, current is flowing, but no current is going through 10 ohm because this is open. So therefore, current will flow through J20 and minus J10. So therefore, first you find out what is the current flowing through this minus J10, and then multiply by minus J10. That will be your voltage across A and B. The 10 ohm will not be counted because this is open circuited. So that's why you see my calculation, what I am doing, V Thevenin, that voltage value, this one 50 angle 30 over the total impedance. This means J20 plus minus J10, this one multiplied by minus J10, because I have to find out the voltage here, ultimately this point and this point. And then if I move forward, so in the denominator, it is J10. So I wrote 10 angle 90 multiplied by, I have written this 10 angle minus 90. So what you can do, I mean, two ways you can express the result. From here directly you can go, I have written here, like 50 angle 30, and then look this one. Once it will go upward, 10 cancel, then minus 90. So you are getting minus 180. But on angle minus 180, this means you just need to put a minus sign before. Minus 50, this one. Because this one in polar form, or if you think the exponential form, e to the power j minus 180. So cosine of minus 180 will give you minus 1. And then sine minus 180, that is 0. So directly you can write minus 50 angle 30. Or what you can do, I have shown the other approach. Look this one, 10, 10 cancelled. This minus 90 is going in the numerator. So minus 90 minus 90 minus 180, but then plus 30. So you can say minus 150. So 50 at an angle of minus 150, or you can express in rectangular for this one, minus 43.30 minus j25. So either you can express this format or 50 at an angle of minus 150. I mean, equally, like you will get the same credit, no problem. Everybody, could you follow this one?
Hey, Doc.
Yes.
I have the same result, but I did voltage division. Is that is a good way to?
I did voltage division as well.
Yeah, so I think that this is the voltage division. So did exactly I did that.
Okay, yeah, I see it, yeah.
You see the first line, yeah. Therefore, current, the voltage, 50 is the voltage, this one. So first I am finding the current, total current. So therefore, this is the total, the current, V over the total impedance. So total impedance is J20 minus J10, because 10 ohm will not be counted. It is open circuited. And then that is the total current. So I did not write, okay, IT. I directly applied the voltage division. Voltage divided by total impedance multiplied by that respective impedance, across which I have to find out the voltage. So therefore, this is essentially the voltage division. So everybody got this result, either minus 50 angle 30 or this one. Did you all get, or you got different result?
I got that.
Okay. And then the J Thevenin value, is it the same you got?
Yes.
Yeah. Okay, great. Yeah. So therefore, again, once again, like I am going to post this on eCoursera under the tab exam. So again, you can have a look. And I believe you all are keeping your hard copy, so you can match where you made mistake. And then soon in a day or two, you will be getting your grade posted. So you will be fully fine. And then once again, as I told you, like if you have any questions, comments, any confusion, anytime, you are most welcome. Please feel free and don't hesitate to contact with me. You can email me anytime. Okay, so moving forward, this one, find J in the network of power 3, given that V0 is 8 at angle of 0 volt. So here there is on voltage source 40 angle minus 90, and then 12 volt minus J4. This is the element. The numbers are not given, the impedance value that you have to find out is J. And then in series there is J8 ohm inductor, across which the voltage V0 is given. So this V0 is this one, 8 at an angle of 0. So with this one, find out what should be the value of J so that the V0 becomes 8. That's the question. So everybody look the circuit. So at first, find out the total impedance. So, I mean, you can apply different approach, no problem. You can apply the nodal equation, or, I mean, two loop. You can find out different way. But other easy approach is that, look everybody, because this is the V0 here. If you can know what current is flowing through J8 ohm, then you multiply that current by J8. And then you say, okay, that equal to this one. Then you will be getting the J value. So therefore, your goal is to find out what is the current flowing through that G and J atom, in this loop. And that current multiplied by this one, that will make the V naught, which is equal to this one. So therefore, to know that, what I did, I first make the equivalent impedance for this circuit. You see, therefore, that G is in series J8, and that combination is in parallel with minus J4, and that whole combination is in series with 12 ohm. That is your total G, or the equivalent G. And then you find out the current. What is the total current? This voltage divided by that equivalent impedance. And once you get the current here, and then you find out the current here, at this point, you apply the current divider rule. Something is going here, and then remaining is going there. So you need to know what current is flowing through this one. Then you are done. You just multiply this one and equate with that, and ultimately you will be getting the value of J. So therefore, everybody say what I am doing here. First, this G plus J8, that is in parallel with minus J4, you see. So therefore, I am with keeping the G as it is, because you cannot do anything. It is the just a letter. You cannot do anything. So therefore, keeping as it is with the J, I just left in that format. You might express different way. And then total impedance, this one plus 12. This you see, 12 plus this combination, which you see my calculation. Then I expressed in that format. And then, as I said, this is my total impedance. Here I am calculating total current. So therefore, that impedance over this, but then I have placed this one in the numerator and this one in the denominator. Just in one step, I have written this one. And then now your goal is to find out how much current is flowing through this J8. So apply the current divider rule here. This means the total current multiplied by this one and divide by this plus this one. Current divider rule. You see here, IJ8. This total current multiplied by that minus J4, divide by that total impedance, series impedance. This means total I minus J4, and then in the denominator I wrote G plus J4. And then you have the total current expression, substitute that on there. And then in one step I have written, because I have got IJ8, this one. So V naught it, IJ8 multiplied by J8. And then what is IJ8? I am substituting this one here and putting that J8. And the total I value, this one total I, everything I substituted. And then that, what is that V naught? V naught is 8 at angle of 0, which was given here, this one, in the statement. So therefore, I equated with that one. And then now I am just calculating. I'm simplifying. So I got this one. And then there is, I think, 2 or 3 more lines. After that, everybody see this one. So because your goal is to find out the G, so I left the G in the left side, and then I transferred everything on the right side. And then finally, this is my G. So in the rectangular form, I got 2.798 minus J16.403, or in polar form, 16.64 angle minus 80.32 degree ohm. This will be your G value. Everybody, could you follow me?
Yes.
Does anybody have any question here? And then did you all get this result? G value, you got the same value or you got different value?
No, nodal analysis failed me.
Yeah, I got a very different value.
Yeah, so
Okay. So,
That particular question seemed like it was one of the hardest ones.
I think number 3 was the hardest.
okay, got it. But could you follow my procedure that I explained?
Yeah, I tried to do the total impedance, and I was like, I have no idea how I'm going to do anything with a letter in here. But then once you said you just
Okay.
do current, it's like, oh yeah, find back. Okay.
Yeah, yeah, yeah. You see, you cannot do with the letter, right? Your calculator will not do anything with the symbol later. So that's a keep you as it is. And that is the thing that you have to find out. That's the question, find J. So
How did you because I calculated total impedance. I did that Z and V, or the current or the volt, the impedance of the inductor is in one branch and is in parallel with the impedance of the capacitor,
yeah,
and then that is in series with the resistor.
yeah, that's right.
And then
Yeah.
I must
This is exactly what I did here. You see my very first line? Look, the very first line.
right.
The G plus J8, this one. This is the parallel sign that is in parallel with minus J4. So exactly I did what you are explaining. Yes, you see? And then that is in series with 12. So after that, what you did?
After that,
Yeah.
I calculated the total impedance, and then let's see, then I calculated the volt or the currents, and after I had the current, I used that to solve for Z.
Okay. So did you calculate this current, the current flowing through G and then J8?
Right. So I calculated the current, I guess I2, I1, and I3. Yeah, I did calculate that current.
Okay, but probably, and then you did not get this same result?
No, I did not.
Then maybe somewhere you made mistake in calculation after that. You lost somewhere. So
Okay.
here you see what I did. Once you calculated the total impedance, you see this expression, including the Z, I am finding the total current. Because look the circuit, once you calculated the total impedance, and then you can find out what is the total current that is flowing through the 12 ohm. That is the first step. So voltage divide by that total impedance, whatever it is. And once you get the total current, then simply apply the current divider rule. You don't need to apply the further nodal analysis or anything. You just simply apply the current divider rule.
What did you get for so for current one, or the current running through the resistor, what value did you get? Did you get 3.33 at an angle of -90?
No, how you are getting the current? You cannot get the current because you see it is in the form of the Z. You see the total impedance. Look my expression.
Oh, right, I see. Yes, okay.
Yeah, yeah. So you cannot get a value that is including that letter G, symbol J. So you will not get a value. So you see total current. Total current is that voltage divided by the total impedance. Just look this one. And then I can just simplify a little bit, but I cannot get rid of the G. Always there will be letter J. And then once I get the total current, at next step you look, I am applying the current divider rule, IJ8. I need to find out the current through this branch because the V0 here, that V0 is given. So I must relate that current to this one. Otherwise, I cannot find out the G because G is in series in this one with this component. So that's why you need to find out the current flowing through J8 or through G, in other words. So once you know the total current, then just apply the current divider rule. What current is flowing through this branch? So that I did. You look, this is total current and then IJ8. Current divider rule, that total current multiplied by the other impedance. When you are finding current through this one, you have to multiply it by this one. If you find out current through this branch, then you have to multiply with this impedance and divide by the total impedance. That is the current divider rule, right, everybody? You see, this is current divider rule. Total current multiplied by the other impedance at which I am not interested in finding the current, divide by the total impedance. So therefore total current minus J4, G plus J4. And then you substitute the total current value here. And then you go ahead, and then V naught, calculate the V naught and substitute the V naught value, which is given in the problem 8 at an angle of 0. Then you will get a relationship in terms of G, still G. And then you look, but you have to get rid of, that's why on the left side I have put the G, and on the right side I have put all the numerical values. And then you'll see, so therefore G is this right side component over this one, 12 minus 4J. Now you can apply the phasor algebra here that I did. Priscilla, now could you follow me?
Yes.
Yes, just look carefully and then see my calculation and match with on. You might do different way, but it's still you should get the same result. As I said, if you
Right.
yeah,
I calculated current going through the inductor.
okay,
Yeah, because we were given the voltage, and so that was the same current going through Z since
okay,
they're in series.
okay. Yes, therefore still you have to relate with the G because that is your task to find the G, right? Yeah. Because the same current is flowing through G8 and then through this G, capital G. So therefore, whatever way you do, like ultimately, like you cannot get rid of the G and you have to find out that G. So is everybody fine?
Yes.
Yes.
Okay, therefore, once I upload, you please again match with your result and where you made mistakes, and then please see. Yeah. Okay, the question number 4 was obtain the power factor of the following circuit. So you see, this is all are like resistance, inductance, and capacitive component. There is no voltage and current source. And so you cannot find out the complex power or apparent power or real power, anything that you will give you the theta and then you apply cos theta. That's why, because all are the impedances, so you have to go through impedance. Therefore, see the basic definition. This is the impedance triangle. This is R, this is X, here the hypotenuse is G. So this means here is the theta. That's the relationship. So this means definition of power factor is cosine theta, which is R over G. And then in terms of power triangle, when it is P here, Q here, apparent power here, cos theta is P over S. Exactly the same. So it depends on how to calculate which things are given. You see, in this case, there is no current, no voltage information. So you cannot calculate the complex power that will include your power factor angle. So you must calculate the equivalent impedance and the angle with the, so you have to look what is the angle and then take its cosine theta. That is your power factor. So that's why everybody see, find out the equivalent impedance. Look, 4 ohm is in series with J1 and then that combination is in parallel with J2. So you see exactly I have written the first line, J2, this is parallel sign, 4 plus J1. And then I simplified, I kept in that format. And that on, this combination is in series with minus J1, that I did, minus J1, I added with that one. And that whole combination is in parallel with 1 ohm. So you see, after that I am making parallel here, this line. And then ultimately I got 0.48 angle 21.54 degree. So this is your this theta actually that is representing. So then make its cosine theta. That is the power factor. So and then I wrote lagging because you got the positive sign here. If you convert into rectangular form, you will notice that it has plus R plus JX, R plus JX. So plus J plus indicates that is the lagging. If it would be minus, then you would be getting R minus JX. Minus sign will indicate the capacitance and then power factor will be leading. So that's why here 0.93 power factor is lagging. Did everybody get this one, the same result?
Yes.
Yes.
Okay, great. Yes, okay. Does anybody have any questions? So therefore, just as I said, just your goal is to find out the equivalent J and then see what is the angle with that J. That's all. Okay, therefore you will be looking. So I have put the solution there. Okay, this one, in the circuit of the following figure 5, G1 is given, G2 is given. Then calculate the total apparent power, real power, reactive power, and then power factor. So you see, this is a parallel circuit, clearly. There are two parallel branches. Here ion current is flowing, through this one I2 current is flowing. This is the total current, ion plus I2, and the voltage is given. So this means that because this is parallel circuit, so same voltage applies across each element. So therefore what I am doing, the VRMS, this one is given. I just gave the name V on 2010, this one. I am finding ion first. So what is ion? That V on over G on. So just V on is given, G on is given. I got 2 at an angle of 40 degree ampere. Next I found out the I2. Again that V on over G2. I got this on 3 at an angle of minus 35 ampere. And then I am calculating the total current. I take ion plus I2. You see, and then of course that is the RMS because our voltage was in RMS. So ion plus I2. So 2 that angle plus 3 that angle. And then after calculating, I got 4.01 approximately, and then minus 6.15 degree. Okay, and then because my task is to find out the apparent power, real power, reactive power, so I am just calculating the complex power, and in the complex, from the complex power, I can easily calculate all these three. I mean, you might do differently, no problem. But what I did, I calculated the complex power, like bold S, capital S, VRMS, IRMS conjugate. So you know this one, complex power, VRMS, IRMS conjugate. So what is my VRMS? My VRMS is this one, which was given, this one, 120 angle 10 degree. And then what is my IRMS? This one, 4.0, and then angle was minus because I have to make conjugate. So I change the sign, it is plus. And then from there I got 481.2 angle 16.15. And then I express this one in rectangular format. But the unit is volt ampere for complex part. So therefore by looking this one, now I am done. What is apparent power? Just the amplitude portion, magnitude portion, 481.2 volt ampere. What is my real power? This one, the real component, 462.21. I mean, in calculator, it depends on how you are doing. You might get a little bit more or less value than this one, 0.1. You might get 0.2324, etc. But the first portion should be the same. And then this is the reactive power, 133.85 watt. And then power factor, just cosine of that angle, 0.96. And again, it is lagging because of the plus sign here with the complex power. So that indicates this is the inductive effect, which provides lagging power factor. If it would be minus sign here, then I would write here leading. So did everybody get these results?
If your results are just a very small incremental difference off, what's the window of acceptable tolerance?
And no, that's fully fine. So as I said, like it depending on calculator. So what, for example, did you get this one, 81.2? So where is the incremental difference that you said, after decimal or?
I got 482, 463, 134.
Okay.
Everything's just up by 1.
Also probably that will be fully fine, fully fine.
Okay.
So you see here, look this on IT, like I just gave 3.99, but I think if
I
you
think I rounded that to 4.
yeah. Then that will probably, that is the reason you got one difference. So you are fully fine. You are fully fine.
Yeah.
Yeah. I mean, as long as your process is fine, like your process is correct, your approach is correct, your equations are correct, even though you made the wrong result, but still you will get the full credit. But if your approach is wrong, for example, complex, you did not make it conjugate here. That is the basic wrong, fundamental error that are. So whatever, even if you get the correct result, but still you will not get full credit if you write the wrong equation. Do you understand what I mean? So if you write the correct equation, if you apply the correct approach, then even if you get the little bit deviated or wrong result, but still you will get full credit. On the other hand, if you go wrong approach, but somehow you get the correct result, you will not get the full credit. So therefore, methodically, in terms of equations, that should be correct. Then you will be fine. Therefore, because I wrote 3.99, I mean, easily you can write this on 4, and that makes sense. And then definitely you will get little bit deviated number here. So then you are fully fine. So everybody, could you follow this one?
Yes.
Yes.
Yes, so please, once again, you look, you match, and then you will be fine. Yeah. And I have properly instructed the grader, then, don't give any 0. So if you, always give some partial credit. I properly, that instructed. So I hope you will be fully fine. Therefore, let's see when he completes, and then I'll let you know. And then once again, like if you have any questions, confusion, then please don't hesitate to contact with me about your grading or the credit. Okay, so I believe everybody will be fine. Okay, stop sharing this on. I think, let me take you to the other file. Okay, everybody, can you see like circuit analysis in the S domain? Yeah.
Yes, sir.
Yeah. So today we'll start the new chapter. So although we don't have much time, but I will just start. I think this is chapter number 14. The application of Laplace technique into the circuit. So S means this is the Laplace. So probably simultaneously you are learning the same thing in, I think, signals and systems course, right? Laplace.
Yes.
And also some of you might have already done even in some math courses, probably the Laplace thing. So, but I think there is little difference from that signals and system course. There basically you learned how to calculate the Laplace transform, how to apply, and then inverse Laplace transform. But here in this course, we will be applying those Laplace knowledge, Laplace technique to solve the circuit problem. Exactly the same circuit that you did in phasor domain or in the RLC circuit. Exactly similar things can be done with the help of Laplace. So that's why, because you all have done, so probably, so you know the definition of the Laplace. What is the basic definition? It is an integral transformation of a function ft from the time domain into the complex frequency domain, giving a function of s. So you all know, I believe, that this is the definition of Laplace. You have a function ft, so its Laplace will be integration of 0 to infinity function of t e to the power minus st dt. And where s is that complex frequency, is sigma plus j omega. So the thing is that this s, that is the important. That s is that important. So therefore here in the s, like here you may assume that sigma is 0. So ultimately your s equal to j omega. Because there is j omega, so still you can see that is the complex frequency. And it is called the complex frequency because omega means the 2 pi f. So therefore, from now on in any circuit, so instead of applying the phasor technique, you can directly apply the Laplace technique. You just need to replace j omega by s, assuming sigma is 0. So therefore, I mean, before going or before looking some example, the first of all, like here I have written, what is the main advantage or what is the significance of that Laplace transform? So you see, I have written 3 important points. It can be applied to a wide variety of inputs than phasor analysis. You see, in the phasor domain or in the phasor analysis, what we did, first we converted time domain circuit into phasor, right? We expressed voltage or current in terms of magnitude and angle. And then we applied the phasor algebra. Fully we applied the phasor algebra. But if you remember, in all phasor analysis problem, what was your input in the circuit? All were sinusoidal only, either cosine form or sine form, but all input were in terms of sinusoid only, sinusoidal function only. There was no other DC or the other thing, step function. But you know what I have written? The Laplace can be applied to a wide variety of inputs. This means your input can be sinusoidal, can be non-sinusoidal, can be DC, can be unit step function, can be impulse function. It can be everything. Square waveform, it can be everything. So that is one beneficial feature that Laplace can handle all types of input. So definitely then, now the thing is that phasor analysis, phasor algebra was applicable only to the cosine or sine waveform. Like when we wrote like V equal to Vm cosine of omega t plus theta, then in phasor form, just V at an angle of theta. And we wrote that on because that was the cosine function. If it would be a DC signal, I mean the non-sinusoidal waveform, then you cannot express it in phasor. That's why we have to take the help of different technique, which is the Laplace transform technique. So this is one benefit, or this is the difference between the phasor domain and then the Laplace transform domain. Now, what I said, it provides an easy way to solve circuit problems involving initial conditions because it allows us to work with algebraic equation instead of differential equation. Now, everybody, for example, for a minute, think about the RLC circuit. What you did in RLC circuit. In RLC circuit, due to a input, due to an excitation, you calculated transient value, you calculated steady state value, and then you got the total result, total response. And you first calculated whether the response is underdamped, overdamped, or critically damped. You calculated alpha omega naught, right? And then depending on the nature of the response, you picked up on equation. But unfortunately, in those equations, always there are two constants like A1 and A2. And how you calculated those constants? With the help of initial condition. And if the initial conditions were not available, then you had to first find out the initial condition. With the help of initial condition only, you were able to find out the constant. But you see, you in this chapter, if you apply the Laplace, you don't need to worry about those points. Laplace, it will include those initial conditions. It is easy. And you can solve everything just using the algebraic equation. You don't need to think about any differential equation. You don't need like dv by dt or L di by dt, C dv by dt. You don't need to do those things. Everything you can express in terms of algebraic equation and just find out the value. So everything will go in terms of the symbol S, which is called the Laplace operator, symbol S. I mean, soon I am showing you example, then you will get fun. and you will understand. And then what I have written, the third point, the Laplace transform is capable of providing us in one single operation the total response of the circuit comprising both the natural and forced response. This means natural means transient response and forced response means steady state response. Therefore, if you remember that chapter 8, RLC transient, it was very long calculation. Always you faced the issue with initial calculation finding, and when there was source present, you found out what is the steady state value, what is the transient value, and you summed up. But here, you did not, in Laplace, you did not think about that. Inherently, naturally, it will include both things. So therefore, these all are the beneficial feature of the Laplace transform method over the Phasor technique or time domain technique or the RLC transient technique. So the main benefit this one, that it can handle with any type of input, not just the sinusoidal waveform, likewise the Phasor technique. Therefore, you don't need to deal with the Phasor analysis. Everything will be in terms of S, symbol S, which is called Laplace operator, and everything will go in terms of the algebraic equation. And then at last, you have to convert back into time domain expression. Therefore, for example, everybody, momentarily, what I am saying, just see this example. I mean, you don't need to solve. First just try to understand what I am saying. For the following circuit, find V naught T, assuming zero initial condition. See everybody, this circuit, this is 1 ohm, this is 1/3 farad, this is 5 ohm, 1 Henry inductor. So I am asking, okay, find out V naught. But then I am saying, assuming zero initial condition, meaning that there is no initial condition given. But you see the input plus minus, I have written UT. So you all know, even from the DC circuit codes, UT means just a step function, unit step function. That is the meaning of UT. So now think about if it would be Phasor analysis and if it would be like sinusoidal function here. For example, Vt equal to 100 something, some angle is given, then easily you can do, right? I mean, you converted this capacitance and this one in Phasor domain, j omega c, and easily you can solve. But from today, we will not apply that technique. We will not go in terms of j omega or j omega c, or like plus j or minus j. We will not go in that way. So therefore, today we will go in terms of S, in terms of Laplace. So therefore, to apply the Laplace for this one, at first, we have to convert the inductor and then that capacitor component into their Laplace domain, So that thing we will be learning how to convert into Laplace domain. But just I am explaining you the background or the motivation of this one, or why we will apply and how we will apply the Laplace, that thing. And then also for this source, we have to convert into Laplace domain. What is its Laplace equivalent? What is the meaning of UT? So once you can express this on in terms of Laplace, so at least you know from signals and system codes, Laplace means it will be in terms of S. I mean, I will also show you a few examples. Mostly I will be emphasizing the circuit, but I will also show you a little bit about calculating the Laplace. So it will be in terms of S. Like for example, for UT, it will be 1 over S. And then we have to express this one in terms of S. This one in terms of S. So there will be no J. You remember, there will be no J. And if there is no J, this means you are fully fine. You will feel comfort. It is much more easier because there is no J and there is no angle. So you don't need to deal with the Phasor algebra. Only you have to apply the simple algebra. That algebra you have learned in your high school or even in the middle school, simple algebra. And then apply all the rules superposition, Thevenin, nodal analysis, voltage divider rule, whatever. Everything is the same, but in the circuit you can see only S and the resistance value as it is. And then at the end, everything will be SSS. At the end, you convert back, you apply the inverse Laplace transformation and express the result in time domain. So that's why you have to know what is the Laplace equivalent of this one, source and then capacitor inductor, and at the end, how you can get back into time domain. This means inverse Laplace transform. That's all. Similarly, you see now, you see before solving the problem, just you understand the meaning that what we want to do and what we need to do. That thing I am telling. Here it was assuming zero initial condition, but see the next problem. For the following circuit, determine IT for t greater than 0, assume V0 minus is 9 volt. So you see this type of problem, you have done a lot in the RLC transient, right? The initial values are given. But here, once you will apply the Laplace technique, you don't need to do in that way. You don't need to write any differential equation or anything. You just need to express this capacitor into the equivalent Laplace domain and the source. Then you are fine. That will automatically include your initial values. And then at the end, you calculate the current I and express in inverse Laplace, express in time domain. Then you will be fully fine. So everybody, could you follow me what I am saying?
Yes.
So
So-
far,
Yeah. So I mean, soon I'll show an example. You will be understanding. So therefore, for example, everybody see for the first problem. Okay, this one was the first problem. So for this one, see what I am doing. First, I am like transforming from the T domain to the S domain. First, I am converting in this circuit everything into the Laplace domain. I mean, how to do the Laplace, that thing we will do later, but first see that what is the approach. First, I am converting this source, this component and this component into the Laplace domain. So therefore, for the source ut, it will be 1 over s. Now, how I will get this one? This one, I think I will discuss in the next class. Today, we don't have time. This is just Laplace transformation. Or I believe you already have learned in signal system codes, but I will be discussing. For 1 Henry, for this one, 1 Henry inductor, the Laplace will be SL, simply it is S. For capacitor, 1 over 3 farad, Laplace value will be 3 over S. Therefore, see everything. Source is 1 over S, inductor S, and capacitor 3 over S. Now this is your circuit. You see, this means this is your circuit. I replaced with the Laplace everything. 1 over S, this is 3 over S, this is simply S. So therefore the question was find out V0. This means if you can find out what is the current flowing through this one and then multiply its respective Laplace, that is your V0. So therefore everybody see, this is my circuit. I need to find out current flowing through this one and then multiplied by the S. So I have written here, you see, V0 S into I2. So what I am doing here, just I am applying, I consider the two loop. In this loop, ion S, in this loop, I2S. See, once you will write down or draw the Laplace domain circuit, current, voltage, everything will be in terms of S. That's why I have written ion S, I2S, V0 S. I mean, this circuit, everything in terms of the S. Once you convert into the S domain, Laplace domain. So therefore, you see the expression, there is no J. There is no J. There is no angle. So because there is no J and no angle, you don't need to apply the phasor technique. You fully forgot the phasor technique. Look, this circuit is simple, the algebra. There is no angle, nothing. Just the number, 1 over S, 3 over S, S5, this number. So therefore, I just wrote down the equation for loop 1. This is the source. If I am going the clockwise direction, so 1 over s is this one plus 1 over s multiplied by ion. But this is also clockwise, I have assumed, but it is going from here to here. So this is minus I2 into 3 over s. For loop 2, I have written down another equation. In this loop, there is no source, so 0. So 3 over s plus 5 plus s in parenthesis I2. But then this one, it is in opposite direction, ion current, so minus 3 over s ion. So therefore, from there, what I am doing, I am just solving. My goal is to find out I2. You have to find out V0. So therefore, I am calculating I2. I got this one. I2 is 3 over s to the power 3 plus 8s squared plus 18s. You see, it's, in the form of the cube or the square, but it's still only the function of x. There is no angle, no j, nothing, only the s. That's why I said you can apply only the algebra. And then from there, I am calculating V0. I am calculating V0. So 3, this is V0. So that current multiplied by the s. So I got this one, but this is in a Laplace domain. You have to express in time domain. That's why you see in the next slide. So I have converted into time domain with the help of inverse Laplace transformation. So finally I got this result. You see, my result is 3 over root 2 e to the power minus 4 to sine of root 2t. Now how I am getting this on, so those things I will be discussing in next class, and how I am writing these things, at the beginning. This means first I will look little bit about Laplace transformation, and at the end I will be learning little bit inverse Laplace transformation. Then you are fully fine. So everybody, could you follow me? How we will apply the Laplace into the circuit problem? Do you understand what I'm saying?
Yes.
Yeah, today I am just giving you the highlight. I am just telling it that how it will look like. Yeah. Next class I will go much deep. We will start from Laplace transformation, inverse Laplace transformation, and then. But at least you are understanding. You see that once you are applying the Laplace, you are converting every component into their respective Laplace. Then it is becoming the function of s only, and just number and then s symbol. So you can apply the algebra and all the basic rules of the circuit analysis. For example, here I am applying just the loop equation. And then that loop equation gave me I2, I got V0. Because it is S domain, I have to convert back into time domain. And then there is technique, that is the inverse Laplace transformation technique. That's all. So therefore, for each and every circuit problem in Laplace, first you have to convert your time domain circuit into the Laplace domain. You have to make a new circuit. And then you see what you have to find out. Apply the simple algebra or standard algebra. At last, you convert that expression into the inverse Laplace to get the time domain function. That's all. You don't need to think about any initial condition. Automatically, everything will be included. So that's why in next class, we will be learning in detail how to get this thing, how I got this one. Today, I'm just showing you what is the essence, what is the importance, or what is the beauty of the applying Laplace. With the help of Laplace, you don't need to do Phasor, you don't need to write any differential equation, you don't need to do anything. Just with the help of the algebra, you can solve everything. That is the thing. Therefore, the problem that you have learned so far, every problem we can apply the Laplace technique. That is the beauty of the Laplace transformation technique. So, okay, everybody. So today, I think we already crossed the time. It is 10:11. So I would like to stop here. But at least everybody understands, right? So what we want to do in this chapter.
Yep.
Yeah. So therefore, next class I will start from the beginning, like how I am converting this on. I will be teaching you this thing, and also the last step how I will convert back into time domain inverse Laplace, and plus much more example and much more problem. Then everybody will be fully fine and you will get fun. Okay, so with that, I like to stop here. Does anybody have any question?